section 2.2. So this was going to be what we were going to do in class today. So I have this document here that we're going to go over, and we're just going to go through both pages together, work through them, kind of talk through what we would talk to, and if you have questions, instead of asking me in class, you can just email them to me. So, okay. First page starts with this idea of a one-sided versus two-sided hypothesis tests. So this comes down to what symbol are you going to use in your alternative. So for example, you see one-sided, so let's do a little drawing here. So one-sided is because this symbol only points in one direction. So a one-sided test is going to connect to a greater than or a less than symbol for your alternative, which remember meant you had some extra idea of how your parameter could be different from this number. So on the other hand, we could have what's called a two-sided test, okay, and that two-sided test on the other hand, let's see if we can move this over. The two-sided test just connects to, let's use a different color, we have the power. Two-sided test connects to this symbol being not equal to, because remember, this is our alternative where we don't know, it could be less or it could be more, we're not sure, so there's two sides to this. We could have both. So two-sided means both less than and greater than. So both of these at the same time, that's what the not equal to symbol means. So we've talked about how to set these up, but we haven't actually really talked about like what changes in the problem, and we're going to go through two problems together. It's the same problem, we're just going to use one-sided versus two-sided to see what happens. So the setup for this, I didn't write it in the document, was this is, here let me write this directly on here for us in case you want to go read it. So this is exercise 5 in 2.1. So that's the kind of basis for what we're doing here. And so you can see that on the screen here. This is the Kelley Blue Book example. I think this has been in a couple problems so far. Kelley Blue Book tells you what the value of your vehicle is depending on how old it is, its condition, stuff like that. So many people use Kelley Blue Book to buy and sell cars, and so we're interested because we want to sell our SUV. Okay, so we have a 2019 SUV we want to sell. Now, what we want to do is we want to try to do a selling price that's similar to what other SUVs are in our area. Okay, so what we do is the first thing we do is we go to Kelley Blue Book and just say, what's the value of my SUV? And so Kelley Blue Book, we can see it starts right here. The average Kelley Blue Book value of a used 2018 to 2020 SUV is 19,560. So that's big. The big population average for these SUVs all over the country is this 19,000. But, it can vary from place to place what the actual cost should be. That's just a big population average. So I'm interested in if that's really right for my area. So, because I want to sell my SUV in my area, and if they're selling for more in my area, I can try to sell for that price. If they're selling for less, well then I probably have to sell for less so that it actually sells. So this value has just given us our parameter, our guess at the parameter, what it could be. Okay, now we need to decide whether our alternative is going to be, no, in our area it's not this, or do we have a specific reason to think, actually, I think in our area it's selling for more. And, we're not going to dive into why you would think this, but, maybe you live in an area that's more expensive. If that's the case, then you might think, well, if I live in a more expensive area, food's more expensive, incomes are higher, housing is more expensive, I might expect cars to go for more money too. That's reasonable. So let's say that's in your head. Well, you wouldn't want to do not equal to here. Instead, what you would want to do, right, is you would want to do greater than, because by that just description that's in your head, you might think, okay, well, you know what, actually, I'm in a more expensive area than the general country. I'm in a, on average, I'm in a more expensive area, so I think the car should go for more. and I want to see if I have evidence to show that that's true so I can put my car up for more money. Okay, so that's the setup of this problem. So let's just jump to the document so we could do some comparison. Okay, so now we can see the two different hypotheses we set up. There's the one-sided, I think I'm in a more expensive area, so my car should be more expensive, or sell for more. That's this one, one-sided. And then over here, we're at two-sided. We don't know. Maybe our area could have cars selling for less or more. I don't really know. So once we have that set up, right, what's the next thing we can do? Well, given our null, we've got our null here, average cost of SUVs is $19,000. Look, it's not different between these two, just something to note. We create the null distribution, or our sample distribution as we've been calling it as well. But remember, all that mattered from that, right, was taking samples like our actual real sample, but assuming the null is true, which is the same between these. So I need the same picture here. The picture doesn't change between these two examples. It doesn't matter if I'm one-sided, two-sided. My picture only relies, right, this is important, my picture only relies on knowing what the middle should be, which is the same in both scenarios. And then also the spread, remember, is determined by your sample size, like how many cars did you actually go view. But we're going to pretend in this scenario that's the same, all right? The number of cars we go view is the same. So to make this picture, I had to tell the computer the exact same things. Hey, computer, assume the average cost for my SUV is $19,560, both scenarios. Okay, computer, now go take samples of that population over and over and over again and tell me what the average price you get is each time. Boom, 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 boom. So I get the same picture regardless. Nothing should change there. Okay, and let's assume I have this statistic. I go and take samples, and I get that when I go take real actual sample of, I forgot to mention it, let's say 20 cars. So I will put that in here. We'll put in that N is 20 cars. And so we're breaking away from the problem in the book here, so I could get a specific number for us to play with. So this is just me made up. I made this number up. This one and this one, just totally made up by me like I usually do in class. So this is going to be our statistic. I went real life, 20 cars, checked out the ads, and found an average asking price of $21,000. Okay, so you would have to, what's your gut reaction? Go take 21,000, look up here, and say, is that near the middle and usual, or is that near the outside unusual? Nothing is changing. You could still kind of do that same idea to both of these. Okay, but there is a change, and here it comes. The next step is, how do I actually figure out usual, unusual? Well, we're going to use the p-value for both of these two scenarios, because the p-value is really good at one-sided versus two-sided. That's what we're going to use almost always when we're doing a one-sided test. And so here's how the p-value looks. And what you'll notice is a difference, okay, between the p-values here. Notice I have the same statistic, 21,750 for both of these. It's right about here, right about here. But this, remember, is a one-sided test, which means I only care about samples that are greater than. I only want evidence that the true average is bigger than what was claimed. So I only care about, remember my alternative was mu is greater than. So I only care about one side here. But over here, this is two-sided. So I'm really interested in collecting information about mu being greater than, or I want information on the possible chance of the average being less than. I want both because it's not equal to. And remember, not equal to means I think it could be bigger, that's the right side, or smaller, that's the left side. So I want to look at extreme examples on both sides here because I don't know which one it is. But if you do that, the p-value is then calculated by counting up all the dots that are as extreme as your sample or more extreme. But in this case, one-sided, I only care about bigger than. That's the only thing I'm interested in. So I only have 40 dots here out of 1,000, which gives me a p-value. Remember, this is your p-value of 4%. Okay, but over here, I want any evidence of greater than, that's this, over to the right, or I want evidence of less than, because it's not equal to, could be either. So I actually am going to count up all the dots over here and all the dots over here. That gives me a p-value of 7.6%. It's more dots because I'm trying to look for evidence of bigger or less than. So this is tricky, but this is the thing we have to remember. If we go from one-sided to two-sided, like in this example, one side to two sides, see 2 here, then we're picking up more dots. And the way that you could try to think about that is, okay, what am I'm trying to get evidence for the alternative. I know we framed this previously as we're doing all this to kind of say, no, I don't like the null. But you want to start shifting the way you think about a hypothesis test instead to, my goal is let's see if we can find evidence for the alternative. But here's the problem. Our evidence, you can't see me quoting, right? Not that I have any idea why I'm quoting this, but my evidence, quote unquote, is the statistic and how usual or unusual it is. But the problem is the statistic stays the same between these two, right? There's no difference. The distribution, that's the same. There's no difference. So it's the same amount of evidence. In the one-sided test, it can go all towards the one side, the alternative. But on the two-sided test, that same evidence, that same x bar, which is our evidence here, right? This is like our evidence to try to show something, our sample. It only has to do one side of work for the one-sided test. But on the two-sided test, that same evidence needs to try to show you both less than and try to show you that it could also be greater than. So what you need to think of it is that same amount of evidence, our sample and its usual unusualness, is kind of split up between two directions here, two-sided. I'm trying to show it could be two things. That's more I have to do. That's more work. My evidence can't go as far because I'm trying to show you two different options. Over here, no, it's only one thing I'm trying to find evidence of, so this is stronger. And we see that in the p-value. If we go back down to the p-value, right? We see that in the p-value. In the one-sided test, this same statistic gets me all the way down to a p-value of 4%. That's unusual. But over here, the same statistic, the same distribution, the same setup, this is usual. Right? Remember, 5% is our cutoff. Smaller than 5%, unusual. Right? We'll put that in a different color. Use too much of this color. Right? Less than 5% is unusual. But usual over here, this changed up. This was bigger than 5%. 7.6 is bigger than 5%. So I didn't quite get you enough evidence to go for the alternative in the two-sided case. But in the one-sided case, I did give you enough evidence. So we got to be careful here. We got to think about this. Two-sided, I told you right at the beginning of doing these, the two-sided was your safe bet. Like if you're really not sure which way to go, just do two-sided. And that becomes the safe bet because you see our evidence doesn't quite go as far in a two-sided scenario. So if you're really unsure, you don't know what to do, just go two-sided. It's the safe bet because that same evidence won't get you as small of a p-value. See, our p-value is bigger over here compared to this. And so we didn't quite hit the cutoff of unusual. And so we're going to say in the two-sided case, right, what's our conclusion going to be for the two-sided case? Just for practice, right? I see usual. I'm going to say null plausible. So because I chose two-sided, I didn't know which one, I'm going to end up claiming, okay, yep, 19,000 could be plausible. Maybe I should just put my value there. That's what at this point, I don't have any reason to believe it's not 19,000. So without any more work or, more sampling or anything like that, I'm just going to say, you know what? I spent enough time on this. I'll just put it up for 19,000, see what happens. Over here, I have a p-value that's 4%, which is unusual. So we are going to look at that, and we're going to say, let's get ourselves another color, unusual. So I'm going to say I have the null is not plausible. Right? Just not because it's unusual. And instead, what we'll say is we have evidence for the alternative. These say the same thing to us, so we could write either one. But specifically, there's evidence for the alternative. Remind yourself, nothing wrong going back up. There's evidence that the average cost in my area is actually bigger than 19,000. So I don't want to put 19,000 for my car. I don't want to, sell my car at 19,560. I want to try to put it up for more money than that. Now, I think your first question off of this might be, well, how much? You just told me more. How much? We need to get to chapter 3, which will come in not too long, and we'll be able to give you a range of values that you can feel confident to put your car up for. Again, we're never going to just give you like this number. Okay, because we're not really talking super specifically about your car. We're not a mechanic or a dealership or a car salesman who can tell you, this is exactly what your car's worth. We're using other cars that are similar to yours that have sold in this area to give you an idea what you could put yours up for, what you could feel confident that you should put yours up for. So that'll come later. That'll come later in chapter 3. We'll do better than this greater than. We'll tell you exactly the range that you should feel really confident is the true average. And then you put a couple extra bucks on that because, come on, people can barter with you, right? Come on. So that's the idea. What do you want to come away with here? One-sided, two-sided. Setups are super similar, but in a two-sided test, the same evidence gets split between less than and greater than. And so it's going to ultimately be weaker. The one-sided will be stronger, and you'll notice that means a smaller p-value between the two. Smaller p-value for one-sided, bigger p-value for two-sided. Now you could run through a bunch of different examples where no matter which sided you do, they're both unusual, or maybe they're both usual, but this was a case where having a specific idea in your head already gives you strong enough evidence to go with the alternative on one side, but if you didn't know kind of where you should be starting from, you would not have strong enough evidence if you went two-sided. So there you go, one side versus two-sided. The p-value helps us get to this. You'll notice, just as a quick extra aside, z-score, standardized statistic, 2SD method, they're not helping us here because inherently the way we created them was to be two-sided, right? Think about the 2SD. We go 2 up, 2 down. That's no good anymore. That's not helping us with this one-sided picture. So that's why when we do one-sided problems, we're going to be using p-values to understand what's going on here. Because that 2SD method idea doesn't really quite extend because there's not 2SD to the left and right in any problem. It's just one direction. But the p-value saves us. Okay, so I would take a little break now if I was you. I would take a break many times before this, actually. I should have said that. But in any case, try a couple of these out in the homework, see where you can get through, and then you'll have, ask me about it on Wednesday. We could talk it over. So then the next thing on this is the significance level alpha. So what did we assume right at the end of the problem here? Usual, unusual, we were comparing to 5%. So the idea of the significance level is, why are we using 5%? can I use something different? The answer to can I use something different is yes. That number of a cutoff you want to use different, that's alpha, the significance level. So let me just make a quick note here, kind of like grounding us. So far in our class, alpha was 5%. This was our cutoff so far between usual and unusual. So this is where we have been up to this point. Oh, I'm going off the screen. Unusual. Did I fit it that time? I did. Excellent. So this is usual versus unusual. Okay, that's been our 5%. We've just said, remember 5%, remember 5%, remember 5%. Well, now we have the ability to change that, and we just have a name for it, alpha. If I don't say anything, 5%. That's the general rule. But in some problems, I will say, let's use a different percentage. Like in the homework, you'll see there's a problem where it says use a 1%, a 5%, a 10% cutoff, and do something. So you just have to pay attention to what you're going to take your, again, p-value and compare to. So 5% in general, but if we're more specific, you got to change the number. So why? Like, why would we not want 5%? Well, the setup and the discussion we were going to have in class was about a jury for a murder trial. So we're going to read through this, and then I want you to just kind of like, here, let's zoom in a bit and get rid of some of this so you're not looking at that too. Okay, let me zoom back out. So you're on the jury, there's a murder trial. Let's go through how this works. To start, you are asked, and this is very, very important, and for the connection and just in general, you are asked to assume that the person is innocent, the defendant is innocent. Okay, you walk in there, they walk in. In your head, this person is completely innocent. That is what you need to be saying to yourself through this whole thing. Now, the problem is, I mean, I'm assuming they tell people this. I've never actually been on a jury myself, but I don't think this is what happens often. But this is what needs to happen. You're starting with the assumption of innocent. Guess what? That's your null hypothesis, right? That's what we've been doing. Start by assuming something is true, and then see what happens. That's how a jury works. So you're going to assume they're innocent. Okay. Then what happens? There's the whole trial. You hear evidence from both sides, and in your head, in your notepad, whatever, evidence is being collected. Facts from the trial are given to you, okay, about the murder, the whatever. And then what you do is you take two things and put them together, okay? Here's what you end up doing here. You take two things. You say, first of all, I'm going to take as fact for a second the null, the person's innocent. I'm going to also take as fact the evidence, right? So all the things that you were presented during the trial, the evidence, you're going to take that as true. You're going to take that they're innocent as true. And then you're going to take these two things and say, okay, is this plausible or not? Is it plausible that the person could be innocent and have this evidence also be true? Or is the evidence so strong that you think no way could this person be innocent and all of this evidence be true? And so you could think to yourself kind of like what the evidence could be. In our stats class, this is the sample and the unusual, usual stuff. But for this example, you just think like, okay, you know, there's a witness who says they saw something. Witnesses actually aren't fantastic evidence in general. That's another stats thing we could look up. But we'll just leave that to the side for the moment. So you got a witness. Maybe there's a motive that seems reasonable. Maybe there's some kind of other evidence that's there. Blurry video camera evidence. And so you're thinking you've got, okay, these things here, motive, a witness, you've got some blurry video. Is it possible that all of those things could be given to you as true and the person also be innocent? So let's stop here and just kind of say exactly what we mean. We are saying to ourselves, okay, the person's innocent. Now, in our brains, can we wrap our head around the idea that the person's innocent and there is some video evidence that seems like it looks like the person at the murder scene, and motive, and a witness who says they think they saw the person? All of those, can they all be true at the same time? Like, what's the chance that could happen? That's stats. That's the idea that we're doing, is that you're taking all of that at once in your head and you're saying, what's the chance that really all of these could be happening? We got all this evidence that's true and the person's actually innocent. So that's this idea of plausible, not plausible, usual, unusual. We've been doing this whole time, okay? Now here's the thing. I just asked you to think about that as, what's the chance, right? And here's what you have to do if you're on the jury, right? And this is the basic idea. The basic idea of this is, if we assume all of this is true, okay, the idea is, what percentage chance that they did it are you okay with? And that's, which is a weird thing to say, but let's just kind of think through it. So you're never going to be 100% sure that this is wrong, that they're guilty, okay? You need to pick out what percentage is your cutoff for saying, you know what, I can't say that this person's innocent because of all this evidence. And I know this is very hard for a murder trial, but the goal in statistics is to have a numerical cutoff for this, okay? What we've been doing so far is, if there's less than a 5% chance of all of this actually being true at the same time, we are going to say to ourselves, guilty. That's the idea. The general idea is, if you assume innocent and then they present you with evidence and you're thinking to yourself, all of this packaged together as truth, what's the chance that that really could happen? Well, I think it's less than 5%. Up to this point, we're going to say, that's not good enough, you're guilty. But are you okay with that? The question right now is, specifically, right here, is this okay with you? Do you think this number should be higher, should be lower? Would you be more comfortable if the decision was based on, and you could just think for yourself, for everyone, would you be more comfortable if instead it was, given all of this is true, they're innocent, and all of the evidence you have, the chance that they're actually, right, that they're actually innocent, that all of this could be true together, if that's less than 1%, then you would say guilty. If you're more comfortable with this statement, then 1% should be your cutoff. Maybe you're not even comfortable with that. Maybe you're more comfortable with, it's got to be 0.1% for you to say guilty. The chance that they could be innocent with all this evidence, right? If that's less than 0.1%, then that's what you need to get to in your brain to be like, yeah, I'll send this person to jail. And that's the way you got to think about this, is not so much these percentages of like you kind of being right, but a good way to think about this is as the percentage chance that you're wrong. And that's where this starts to get a lot heavier and a lot more, I think, important, is this number that you choose as your cutoff directly describes the percentage chance that you could be wrong. And that's very important. So if you choose this cutoff, 5%, then what you're saying is, I'm okay with basically a 5% chance of this person being innocent given this evidence. I'm saying, like, I'm okay with that being the percentage chance that really they are innocent for me to say guilty. So if any jury trial hits this cutoff of 5%, and you're like, yeah, of course they could be innocent, I can't be 100% sure, but the chance of them being innocent with this evidence is to me, it's less than 5%. So guilty. And you would expect everyone else on that jury to also snap their fingers guilty at that point. You've got to be comfortable with that if that's your cutoff. If you think that, wait, 5%, that's too high, then you've got to go down to 1%, and then you got to think about that. And the idea being, what if you mess up? Right? What if you mess up? If you mess up, what happens? If you mess up, you send a person who is guilty to jail who's actually innocent. That's what, if you mess up and make the decision here, okay, the evidence together with assuming they're innocent, there's less than a 5% chance of that, I'm going to say guilty. Well, what did you just say? You just said, even though it's less than, there's that percent chance that they're innocent. And you're just saying, like, nope, I know that that's true, but it's so small, I'm just going to say guilty. That's how this system works. So inherently, because of the math, if you're okay with 5%, you are going to be sending, not you, because you're not always on the jury, right? But the royal you, the royal we as a society using the system are going to be sending innocent people to jail. It just so happened that there was all of this evidence that convinced people to get to this 5% cutoff, and it could have been happenstance or a lot of other things. The evidence could be fabricated. The evidence could not actually be as convincing as people think it is. That's a very big one for sure. But in any case, the evidence was presented, assumption was supposed to be assumed, and given those two things, people were sure enough that the person did it to say guilty. But it's all about sureness, because no one can ever be 100% sure. And so we expect to send some people to jail who are innocent. That's the way that this statistical setup works and how our actual system is set up. So that's something you have to think about. 5%, is that good enough? Do you want it to be 1%? Less. Now, the last thing we have to talk about here is your initial gut reaction to this might be, well, of course, just make this number smaller, right? If you're telling me this number kind of gives me an idea of the percentage of people I'm going to send to jail who are innocent, like, I got to make this number small. I think any, human being with emotion would say, I want to make this number small. I got to send as few people to jail who are innocent as possible, of course. But there's a problem. The problem is, if you make this number smaller, then you are increasing the chance of doing the reverse mistake. What's the reverse mistake? Well, this mistake that's given to us by this number, this percentage, this alpha, is I sent an innocent person to jail. That's mistake one that this is talking to us about. You make that, the chance of that smaller, great. But you actually, flip side, instead, if you make it much harder to convict a person, you're going to increase the chance that a guilty person goes free. Just kind of think about that for a second. Lowering your alpha, 0.1% makes it harder to convict an innocent person. Woohoo, great. But the harder you make it to convict an innocent person, the easier you're going to make it, okay, to let someone go who's actually guilty. Because there might be people who are guilty, but the evidence just isn't, quite as convincing, even though they are guilty. And so you taking this cutoff and dropping it might make that person who really didn't have the strongest evidence but was still guilty, now they get to go free because you dropped that cutoff down to try to help people who are innocent. And that's a whole nother can of worms discussion, right? Which of these is worse? If, we're in class together, I think we would have a lot of people just kind of not wanting to say anything because this is a very difficult discussion to have, but this is why this alpha is sometimes so important, because it helps us define the chance of making a certain mistake. Some mistakes are, have basically no consequences. Is this coin fair or not? Who cares? Right? Who cares if this coin is fair or not? Really doesn't matter. Is this person guilty or not? That one has consequences. You choosing a different cutoff for everyone to have or you to have has consequences. So that's why we have different cutoffs for different scenarios, because each scenario has two things you can do wrong, right? You can go with the null is plausible, and really, nope, it's the alternative is true. That's the first one. Or you can go, I feel good about the alternative, no way to the null, but actually, oops, the null was really true. So you got those two options that you can kind of have happen to you. This number here, our cutoff, gives us control of one of them, but unfortunately, it has the opposite negative effect on the other mistake you could make. So, something you just have to think about. Okay? So, something to kind of try to think through there. I know that that's a heavy discussion thought to have. If you want to just kind of come out of this with like, what am I going to need to do? It's actually much, much simpler and straightforward than the discussion here. The idea for this, the general idea is, what have we done so far? P-value, we've compared it to our alpha. If our p-value is less, unusual. Okay. If our p-value is bigger, usual. Right? This is what we've done so far. This doesn't change. This is the exact thing that we did down here, up here. 4% less than 5, done, unusual. 7.6 bigger, usual, done. That process, literally same thing. We're just going to have to be careful in each problem to write down, is it 5% or is it some other number we're comparing to? 1%, 10%, somewhere in between. That's it. That's all you're going to have to change up for problems in the future. It's like right at the end of your analysis with the p-value, what do you compare to? 5%, or did we give you something different in the problem? So that's really all you need to get out of this idea. But it is interesting and valuable to think about what these numbers actually represent. And I think that's a valuable thing to do. So give this computer homework some look over, play with these ideas, and if you have any questions on Wednesday, we'll go over them together. See you then.